Hello, I'm Sebastian. Welcome to 9R Trees podcast. Today, I will summarize and review the book. Something Deeply Hidden by physicist Sean Carroll is a popular science guide to one of the most unsettling questions in modern physics, what quantum mechanics is saying about reality. Instead of treating the theory as a set of calculation rules, Carroll argues that we should take it literally, following the implications of the many worlds interpretation. The book lays out why quantum phenomena such as superposition and entanglement appear strange, how measurement creates puzzles, and why decades of debate have produced many competing stories about what is really happening. Carroll connects these interpretive issues to current research topics, including the arrow of time, quantum information, and the possibility that space-time itself emerges from deeper quantum structure. Written for curious non-specialists, it blends conceptual explanations with a candid tour of the scientific and philosophical stakes. The result is both an introduction to quantum foundations and a case for a specific, realist view of the quantum world. I will give you key takeaways from this book. Firstly, quantum mechanics as a description of reality, not just a tool. A central theme is the difference between using quantum mechanics to predict experimental outcomes and using it to describe what the world is like. The theory delivers astonishingly accurate predictions, yet its standard classroom story often leaves the meaning of the wave function and the role of measurement unclear. Carroll frames this gap as a real scientific problem. If the laws are universal, they should apply to measuring devices and observers just as they apply to electrons. From that starting point, the book clarifies the basic ingredients of the quantum framework, states, probabilities, superposition, and entanglement, while emphasizing how these features depart from everyday intuition. It also explains why the measurement problem arises when one tries to combine a smooth, deterministic evolution of the wave function with the apparent randomness of outcomes. By treating the wave function as physically real, not merely bookkeeping, the discussion motivates why interpretation matters, and why different interpretations make different claims about ontology, causality, and what counts as an acceptable explanation. This topic sets the stage for the many-worlds approach as a straightforward way to keep the mathematical core intact without adding ad hoc rules. Secondly, the measurement problem and why collapse is controversial. The measurement problem is presented as a tension between three ideas. The wave function evolves according to a precise equation, measurements yield definite outcomes, and the wave function is a complete description of a system. Traditional accounts often add a collapse postulate that abruptly selects one outcome when a measurement occurs, but this move raises questions about what qualifies as a measurement, where the boundary between quantum and classical lies, and why collapse should be a fundamental process. The book surveys how this controversy has shaped quantum foundations, highlighting the difference between pragmatic calculation and explanatory clarity. Carroll stresses that the difficulty is not philosophical nitpicking, but a mismatch in the rules one uses depending on context. He explains why collapse proposals invite extra structure and parameters, and how they may create conflicts with the idea that physics should be universal and simple. The discussion also introduces alternative strategies, such as hidden variables and objective collapse models, primarily to contrast them with an interpretation that keeps the core dynamics unchanged. Understanding the measurement problem in this way makes the many-worlds option feel less like science fiction and more like a conservative choice about equations. Thirdly, many-worlds as a literal reading of quantum theory. Carroll argues for the many-worlds interpretation as the most direct way to take quantum mechanics seriously. In this view, the wave function never collapses. Instead, when interactions that look like measurements occur, the combined system of observer, apparatus, and environment becomes entangled, producing distinct, effectively separate branches. Each branch contains an observer who experiences a definite outcome, even though the underlying evolution remains continuous and deterministic. The book explains how this branching is not a mystical splitting of the universe, but a consequence of standard quantum dynamics applied to macroscopic systems. A key part of making this intelligible is clarifying what a world means, not an additional ingredient, but an emergent description of stable patterns within the wave function. Carroll emphasizes that many worlds changes the narrative about chance. Probability becomes about the distribution of outcomes across branches and about rational expectations for observers inside the theory. By framing many worlds as minimal, realist, and compatible with the mathematics that already works, the topic builds an interpretive case that is meant to be both scientifically disciplined and conceptually satisfying, even if it challenges common intuitions about uniqueness and identity. Fourthly, decoherence, emergence, and why classical reality seems stable. A major obstacle to many worlds is the worry that we do not observe blurry superpositions in everyday life. The book addresses this through decoherence, the process by which interaction with the environment rapidly spreads quantum information, suppressing interference between different branches. Carroll explains decoherence as a physical mechanism, not a collapse, showing how it makes different outcomes effectively unable to affect each other. This is what gives branches autonomy and makes classical behavior emerge for macroscopic objects. The discussion connects decoherence to the idea that classical reality is an emergent approximation, the same way temperature emerges from microscopic motion. In this account, definiteness is not a fundamental axiom, but a practical feature of certain stable, redundancy-rich states that persist under environmental monitoring. The book also highlights why emergence is not hand-waving. It is a structured relationship between levels of description. By focusing on how patterns become robust, and why observers inside the universe naturally describe a world with well-defined objects and histories, this topic explains how many worlds can be compatible with the ordinary experience of a single outcome while retaining a purely quantum underlying ontology. Lastly, from quantum information to the emergence of spacetime beyond interpretation, the book explores how quantum theory may illuminate deeper questions about the structure of the universe, including the nature of spacetime. Carroll discusses the modern perspective that information, entanglement, and the structure of quantum states can be more fundamental than the geometric picture we learn from classical physics. This line of thought appears in multiple research programs that suggest space-time geometry might arise from patterns of entanglement and relationships among quantum degrees of freedom. While staying at a conceptual level, the book sketches why gravity and quantum mechanics are difficult to reconcile, and why emergent spacetime is an attractive idea in the search for quantum gravity. The many-worlds framework fits naturally with this direction because it treats the universal wave function as the basic entity, with higher-level structures, including classical worlds and possibly spacetime itself, arising from it. This topic broadens the scope from the measurement problem to cosmology and fundamental physics, emphasizing that interpretive clarity can influence how researchers think about the early universe, black holes, and what counts as a complete description of nature. In conclusion, this book is best for readers who enjoy big-picture science, have some comfort with abstract ideas, and want more than a list of weird quantum facts. Curious non-specialists, philosophy-minded readers, and students looking for a coherent narrative about quantum foundations will find it especially valuable. Its benefit is not only learning vocabulary like superposition or decoherence, but gaining a disciplined way to think about what physical theories claim and what it means for a concept to be emergent. By presenting many worlds as a serious, minimalist interpretation, the book invites readers to reconsider randomness, identity, and the relationship between observation and reality, ideas that can sharpen critical thinking well beyond physics. It is worth buying compared to similar quantum introductions because it is both a primer and an argument, tying technical concepts to a clear stance rather than staying neutral or relying on vague mysticism. It also connects foundations to modern themes like quantum information and emergent spacetime, giving readers a sense of where today's deepest questions might lead and why interpretation can matter for future theory building. If you would like to support Sean Carroll, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.